Hello students, in this video we are going to talk about complex roots of unity, right? We will see that they also form group under the multiplication of complex numbers, right? For this we are going to consider an equation x cube equal to 1. Okay, we will try to see what are the roots of this equation, right? This equation can be written as x cube minus 1 equal to 0. So obviously one root of this equation is x is equal to 1, because when x is taken as 1 minus 1 is equal to 0. So x is equal to 1 is the one of the root. So if we want to find out rest of the two roots, okay, we will have to apply long division or synthetic division, right? So see here, rest of the two roots will be given by which equation? So coefficients of this equations are 1, 0, 0, minus 1. Synthetic division we are applying. We have learned about this in last class, in elementary classes, right? Or in place of this you can also apply long division. Okay, so one root is 1. So now you see 1 as it is, 1 multiplied with 1 we get 1 here, 1 1 multiplied with 1 we get 1 here, 1 1 1 1 1, and we get 0 here. It shows that 1 is the root of given equation. So now rest of the two roots will be given by this equation: 1 plus 1x plus 1 equal to 0. So rest of the two roots will be given by x square plus x plus 1. It is nothing but it is the quotient when x minus 1 is divided by x minus 1. Okay, I mean to say, if I multiply this equation with x minus 1 we get x cube minus 1. Okay, so if one root is given by this equation, rest of the two roots will be given by this equation. Okay, so I'm just erasing this. So that's why I'm saying that rest of the two roots will be given by this equation. Now you see, this is a quadratic equation. So root of this equation is minus b is 1 here, plus minus root b square 1 minus 4 into 1. Okay, 4 into ac, so a and c is 1 and 1. Okay, divided by 2a. Okay, so 2 times a, that is 1. Okay, so now x is equal to minus 1 plus minus 3 iota divided by 2. So so the roots of given equation x cube equal to 1 is x is equal to 1, it is the one root. Second root is 1 plus 3 iota divided by 2, and minus 1 minus 3 iota divided by 2. Okay, so we call this root omega. Okay, we can write, we used to write when we are working in cube root or an x cube equal to 1, we used to call this thing omega. Okay, you just check, if you square this, okay, we get this complex number. Okay, I mean to say it is equal to omega square. If this is omega, then this is omega square. Then these three roots, these are the roots of which equation? X cube is equal to 1. That's why these three roots are called cube roots of unity. Cube roots of unity. Okay, So cube roots of unity are 1 omega omega square. If I take this as a set, then this is a group. Okay, question can be asked in this form: prove that cube roots of unity of unity means 1. Okay, cube means equation is cubic. Okay, cube roots of unity, that is 1 omega omega square, form an abelian group, right? So let us see at the solution of this problem. Okay, so see here, given set is G is equal to 1 omega. Okay, you can call this G, no problem, omega square. Okay, so firstly we are going to prove for all those 5 property now. Okay, so first property is property 1, closure property. So we are having only 3 element here, so this group is a finite group of, okay, if we this is a finite set, or you can after proving it a group, we can call it a finite group of order 3. Okay, so closure property. So see here, if 1 is multiplied with omega, what is result? Omega, right? If 1 is multiplied with omega square, what will we get? What we will be getting? Omega square. If 1 is multiplied with 1, we are going to get 1 again. So see, multiplication of this, all this is multiplication of this is omega, which is also part of G, multiplication of this square, omega square, which is also part of this, and 1 is also part of this. So for this, these numbers are closed. Also you see, omega time 1 is equal to omega, and omega into omega is equal to omega square. Omega into omega square, it is equal to omega 3. Okay, or some of you might be thinking that this is not the part of G. Okay, but it is part of G. Why it is part of G? So see here, since omega is the root of x cube minus 1, right? Omega is the root of x cube equal to 1, or you can say omega is the root of x cube minus 1 is equal to 0. So this implies omega satisfy this equation. So omega cube must be is equal to 1 here, because omega is the root of this equation and omega must satisfy this equation. So omega cube is equal to 1. So it is equal to 1, right? And 1 is the part of G. So obviously it is also part of omega into omega square is part of G. Okay, now nextly you see, omega square into 1 is equal to omega. Omega square into omega is equal to omega cube, which is equal to 1. Omega square into omega square, okay, it is equal to omega 4. Omega 4 can be written as omega 3 into omega, which is equal to 1 into omega, which is equal to omega, right? So you see, we have taken all the possibilities of multiplication in this case, right? So you see all the elements, all the result. Okay, this is this. Okay, these all are part of G. Therefore we can say this set is closed under the multiplication. Okay, multiplication of complex number. Now second property is associativity. Okay, you can say associative law. You will have to write this write in this, since all the complex number, okay, since all the complex number satisfy associative law, okay, therefore this set must also satisfy associative law. You just end this like with this statement. Okay, Now 3, property 3, existence of identity. Okay, you see what could be identity in this case. Okay, the Berry fitting element for the identity in this case could be 1. Okay, you see 1 into omega, firstly you see 1 into 1 is equal to 1 into 1 is equal to 1, right? 1 into omega is equal to 1 omega, and omega into 1 is equal to omega again. Also you see 1 into omega square is equal to omega square, and omega square into 1 is equal to omega square again. So you can you easily figure out that 1 is acting as an identity in this case. Therefore identity exists. Now come to the inverse part. Now property for existence of inverse. Okay, so see what is inverse of 1. Inverse of 1 is itself, right? So what is inverse of omega? If you multiply omega with omega square, we get omega 3, which is equal to 1. So we can say inverse of omega is omega square. Okay, because for inverse what we should get, inverse b is called inverse of a if a time b is equal to identity element. Okay, so here identity element is identity 1. Identity element is 1 here. And you see what is inverse of omega square? Inverse of omega square is omega. Okay, so inverse of all the elements exist in this case. Therefore existence of the fourth property, existence of inverse, is also satisfied. Now you see fifth property, commutative law, because we have to prove that given set is a abelian group, right? So for commutative law you see a into b is equal to b into a for all. Okay, commutative law is true for all the complex numbers, so it must be true for the given set also, because all three numbers are also complex number, right? So you just write this thing in commutativity. So thus we come to know, thus this given set is a abelian group of order 3. Okay, now moving ahead, we are going to talk about fourth root of unity. Now fourth roots of unity. Okay, for this we are going to take equation x4 is equal to 1. Okay, all the roots of this equation are known as fourth roots of unity. Okay, this can be written as x4 minus 1 equal to 0. Now we know a minus b into, okay, a square minus b square is equal to a minus b into a plus b. Okay, so using this formula here we get x square minus 1 x plus 1 is equal to 0. Now we can write it as, since we know I square is equal to minus I square is equal to how much? Plus 1. Or you see iota square is equal to minus 1, or we can write this thing as minus I square is iota square is equal to 1. Okay, so instead of 1 I'm going to write it x square minus iota square is equal to 0. So again applying the same formula, it could be written as x minus 1 plus into x plus 1 and x minus iota x plus iota is equal to 0. Therefore for all four roots are 1 minus 1 iota minus iota. These are the four roots of unity. Okay, so this set also forms a the set 1 minus 1 iota minus iota also forms abelian group, okay, under multiplication, right? So I'm just labeling this to this as an exercise for you, okay. I hope you will do it by your own, okay. So he see here, it is pretty simple again, 1 into 1, okay. If you multiply any two, okay, any two numbers from this set, you will be getting again the number of same set. Like if you multiply I into minus I, what you are going to get? You are going to get minus I square, which is equal to 1, right? So 1 is the element of this set, okay. If you multiply I with I, you get I square, which is equal to minus 1, okay. Minus 1 is also again the element of this set, okay. So you see, this is this set is closed. Also associative law is true for all the complex numbers, right? And third property is existence of identity. One will be acting as identity in this case, and third is inverse. You see, one inverse of 1 is itself, and minus 1 का इनवर्स क्या हो जाएगा? माइनस 1 खुद हो जाएगा. और i का इनवर्स क्या हो जाएगा? i का इनवर्स हो जाएगा ये माइनस आई, और माइनस आई का इनवर्स क्या हो जाएगा? आई. सो इनवर्स ऑफ ऑल द एलिमेंट्स आर इज इनवर्स ऑफ द ऑल द एलिमेंट्स of this set exist. And lastly, you see commutative law. Commutative law is true for all the complex numbers, so it would be true for the true for this set also, okay. This was the fourth roots of unity. Now we will see nth root of unity, okay. Nth roots of unity, okay. So roots of x raised to power n minus 1, or you can write this is an equation, right? All the roots of this equation is known as nth root of unity, okay. So we know one thing, okay, a Euler theorem, that e iota theta is equal to cos theta plus iota sin theta, right? We know this. Can you tell me what is e raised to power iota 2 pi? Okay, it would be equal to cos 2 pi plus iota sin 2 pi, right? So cos 2 pi is equal to 1, and this is equal to sin 2 pi is equal to 0, right? So it is equal to 1. So we can say this is the one root of this equation, right? This is not only one root, it would be having too many roots. It would be having n root, okay. First root is 1, second would be exponential, okay, 2 pi I dividing it by n, okay. If you place this thing here, what we get? Okay, see, if you place this thing here, you are going to get e raised to power 2 pi I divided by n whole power n. It is equal to kitna? N cancel, e 2 pi iota, which is equal to 1, as we did here, okay. So this is the root of given equation. Again, you see, next, e raised to power 4 iota is also root of this equation, because this would be 4, now this would be 4, and this is again 1. So this would be going up to e raised to power n minus 1 2 pi I divided by n, okay. So these are the n roots of given equation. So nth root of, we can write nth roots of unity are 1 e raised to power 2 pi iota divided by n, exponential 4 pi iota n, okay, up to so on, e raised to power n minus 1 2 pi iota divided by n, okay. These are the n roots. If I take alpha is equal to e raised to power 2 pi iota divided by n, then this equation becomes 1 as it is. This we have taken alpha, and this becomes alpha square, okay, and this becomes alpha n minus 1. These are the, so nth root of unity can be written as 1 alpha, alpha square up to so on alpha n minus 1, where alpha is exponential 2 pi I divided by n. Okay, so this group also forms this set also forms an abelian group. Okay, right. So this is all about the complex root of unity. Okay, you can see if you the first example was having order 3, second example was having order 4, and this group, okay, if you say ki this is a group, okay, G, order of G here is n, okay, order of G is n, and this is a finite group, okay, finite abelian group, okay, of order n. So now we are going to talk about general linear group. Okay, general linear group. Okay, this group is represented by GL and R. Okay, actually this group is a group of matrices. Okay, matrices of non-zero determinant, non-zero determinant, right? And n represents here order of the matrices. Okay, that is these matrices are having n by n order, and R represents the entry which these matrices are taking are real numbers. Okay, this represents real number, right? Okay, so this also forms a group. Let us you can be also asked in this form, show that the set of all n by n matrices having non-zero determinant, or you can be in place of this you can be asked non-singular. Okay, these are not okay, non-singular matrices. Non-singular matrices are those matrices whose determinant is not equal to 0. Okay, determinant over reals under the operation of, show that the set of this over the reals under the operation of matrix multiplication is a non-abelian group. Okay, this group is known as general linear group. Okay, it is represented by GL and R. Okay, now we are going to prove this result. Okay, so solution, let G be the set of all n by n matrices. Okay, I'm just writing non-singular matrices. Okay, non-singular matrices, or you can say whose determinant is not equal to 0, okay, over the reals. So now in order to prove this, we will have to prove all four properties, right? So first property is closure property. For this, let a comma b belongs to G. Since we are taking two elements from G and G is a set of matrices, G is a set of all those matrices, all matrices, all non-singular matrices, right? So therefore we can write determinant of A is not equal to 0 and determinant of B is not equal to 0. So we will try to see that whether or not determinant of AB is 0 or not. Okay, so see here, determinant of AB is always equal to determinant of A into determinant of B. Since these both the numbers are not equal to 0, therefore it is also not equal to 0. So this implies AB, determinant of AB is also not equal to 0, which implies AB is also non-singular matrix. Okay, if this is non-singular matrix, we can say AB belongs to G, right? So first property is true. Second, associative property. Okay, in this you write the matrices obeys associative law under the matrix multiplication, right? So therefore it is also true in this case. Now third property, existence of identity. Existence of identity. We know there exists a matrix I, okay, belonging to G because determinant of I is not equal to 0. What is the determinant of I? Determinant of I is 1. Okay, so that's why I'm writing it that I belongs to G. It is a non-singular matrix. We know there exists I belonging to G such that I A is equal to A I. Therefore I acts as identity in this set. Okay, now fourth property, existence of inverse. Okay, existence of inverse. Let A belongs to G. Okay, we are going to find out inverse for this. Okay, this we are going to find out inverse for this matrix, right? And since it is belonging to this G, therefore A is non-singular matrix, which means determinant of A is not equal to 0. When determinant of A is not equal to 0, this matrix is always invertible. I mean to say it inverse of this matrix could be found out, and inverse of this matrix is equal to 1 over determinant of A adjoint of A into adjoint of A. And also you see determinant of A inverse is equal to 1 upon this, right? So this implies A inverse is also non-singular, that is determinant of A inverse is not equal to 0 and A inverse A is equal to I equal to A inverse. Therefore existence inverse. Okay, therefore you write therefore inverse exists, right? So thus we can show thus we can say that given, therefore we can say given set is a group. Okay, but it is not a abelian group because for matrices AB is not equal to BA. Okay, you can give example to show this. Okay, so at last you can write therefore given set, or you can write GLNR is non abelian group, okay, under matrix multiplication. Okay, so next group we are going to study now is special linear group. Okay, special linear group. This group is represented by SL and R. Okay, again N is the order of the matrices and R is the entries. Okay, R means entries of the matrices are from real numbers, right? So this is a matrix, this set is a this group is a set of matrices, set of, okay, you can write instead of set, group of matrices whose determinant is equal to 1, and last determinant was not equal to 0. Okay, it could be 1 2 3, 1 by half, 1 by 2, okay, whatever, but in this case we are going to take only those matrices whose determinant is equal to 1, right? So we can say, and this is also a group, okay, right? So we are going to prove it now that this set forms a group, right? Or in question you could be asked in place of this, you can be also asked that prove that SLNR is a non-abelian group under matrix multiplication, right? Or you could be asked, alternatively you could be asked the set of, prove that the set of, prove that the set of n by n matrices, having unit determinant over reals, okay, forms, okay, forms a non-abelian group under operation of matrix multiplication. Okay, so proof now or solution. Let G is equal to SLNR, okay, equal to set of all n by n matrices having unit determinant, or you can say determinant is equal to 1. Okay, we have to show that G forms a non-abelian group under the composition of multiplication of matrices, right? So for this we have to prove that all four properties. So first property is closure property, For closure property, we are going to take two elements from G. Okay, these two elements are taken from G or SL and R. Since these two elements are taken from SL and R, that means determinant of A is equal to 1 and determinant of B is equal to 1. You see what could be determinant of A and B. So it is equal to determinant of A, determinant of B, which is equal to 1. 1 into 1 is equal to 1. So this implies AB is also a matrix of unit determinant. Okay, this implies AB belongs to SL and R, or you can write G, because G we have taken equal to SL and R. Okay, now second property is associative law. Associative law. Okay, since all the matrices obeys associative law, therefore this set must also obey, this set also obeys associative law. Okay, so you can write this statement in under this associative law thing. Okay, so next is existence of identity. Existence of identity. Okay, so there exists a unit matrix, I equal to in. Okay, belonging to, okay, in means order of identity matrix is n by n. Okay, belonging to G. Why it is belonging to G? Because determinant of I is equal to 1. Therefore it is also the matrix having unit determinant. Okay, so therefore I'm writing that I belongs to G. Okay, because determinant of I is equal to 1, and there exists unit matrix I belonging to G such that AI is equal to A. Okay, in either way, right? So therefore existence of identity. Okay, therefore you can write, therefore I belonging to G works as identity. Okay, identity element for G. Okay, now last is existence of inverse. Okay, so let A belongs to G. Okay, we are going to find out inverse for this element. Okay, we know since it is belonging to G, therefore determinant of A is equal to 1. Okay, we know A inverse is equal to how much? 1 over determinant of A, because this determinant is not equal to 0, so this matrix is invertible, and inverse of this matrix is equal to 1 upon determinant of A into adjoint of A. So it is equal to, this is equal to 1, so inverse is equal to adjoint of A. So inverse exists in this case. Also, what is determinant of inverse? In determinant of inverse is 1 over, this is the determinant. Since it is equal to 1, so 1 upon 1 is equal to 1. So therefore we can write determinant of A inverse is equal to 1. Okay, so therefore A inverse belongs to G, and A inverse is equal to I. Okay, because determinant of this is also 1, therefore it belongs to G, and also since it is inverse, so A into A inverse is equal to identity element. Thus inverse is exist. Okay, so inverse also exist now, but AB is not equal to BA for all the matrices, right? Therefore, given set G is equal to SL and R, that is special linear group, is a non-abelian group under the operation of matrix multiplication. So this was all about special linear group. Okay, now I would like to tell you something about multiplication modulo n. Okay, in last video we did multiplication modulo n, right? And also we saw there, right, that ZP or JP, okay, equal to 1, 2, 3 up to so on, P minus 1 is a group, is a abelian group of order P minus 1. Okay, we did it in last video, right? So this group is also represented by UP. Okay, this group is also represented by UP. I just want to discuss a case with you here. What if, so we saw that, okay, we saw that 1, 2, 3 up to so on, n minus 1 is a group, okay, is a group if n is equal to P, okay, or n is equal to prime number, right? We did this, okay, 1, 2, 3 up to so on, n minus 1 tak, this set forms a group if n is a prime number. So if n is not a prime number, what if n is not a prime number, then will this be a group? Okay, this is the case I'm going to discuss with you in this part of the video, right? So if n is not a prime, okay, we are going to take a case if n is not a prime, then un, okay, let me tell you this one more time, okay. This is bit complicated, okay. Okay, in last video we saw that this set for up to so on up to n minus 1 is a group when n is a prime, okay. If n is not a prime, if n is not a prime, then it is not a group, okay, then it is not a group, okay, not a group. Why it is not a group? Because for example, if you take n is equal to 6, okay, so take z6, okay, so z6 is equal to 1, 2, 3, 4, 5, okay, so we are going to take these two elements. So 2 multiplication modulo 3, okay, is equal to 6, and we know 6 is equal to 0 in multiplication modulo 6, Okay, this is multiplication modulo 6. Okay, so 2 multiplication modulo 6 3 is equal to 0, right? Because when 6 is divided by 6 we get 0 as the remainder, so it is equal to 0, right? So therefore 0 is not the part of this set, so therefore this is not closed, right? Therefore we say 1 2 3 up to 4 n minus 1 is a group when n is a prime. If n is not a prime, then how we are going to make this a group? Okay, if n is not a prime, then we will have to take only those numbers which are co-prime with n, right? Which are co-prime with n. So this group is known as un. Un is okay, all the elements x. Un contains all elements x such that x is co-prime with n. Okay, right? So now I'll tell you what is co-prime. Okay, what are co-prime numbers? Co-prime numbers are those numbers, okay, we call the two number co-prime if GCD of x and n is equal to 1. If GCD of two numbers is 1, then we call those two numbers co-prime. And what is GCD now? For GCD, I'll make you understand with the help of an example. Okay, let us take two numbers 12 and 16. What are divisor of 12? 1 2 3 4 6 and 12 itself. What are divisor of 16? 1 2 4 8 and 16. Now you see what are the common divisor. Common divisors are of both the numbers 1 है, 2 कॉमन डिवाइजर है, 3 नहीं है, 4 भी कॉमन डिवाइजर है. ओके, 4 भी कॉमन डिवाइजर है. अब इनमें से सबसे बड़ा कौन सा है? ग्रेट, दैट इज नोन एज ग्रेटेस्ट कॉमन डिवाइजर. इट इज 4. ओके, 4 is the greatest common divisor of 12 and 16. So we write GCD of 12 and 16 is equal to 4, right? So if GCD of, so for example, if you take 3 and 4, these are two numbers, and GCD of 3 and 4 is equal to 1, right? इसमें कॉमन डिवाइजर कुछ है ही नहीं. ग्रेटेस्ट कॉमन डिवाइजर इज 1 ओनली, बिकॉज इनका देखो 1 का कॉमन डिवाइजर क्या क्या है? 1 है, 3 है. सॉरी, 1 का डिवाइजर क्या क्या है? 1 है और 3 है. 4 का कॉमन डिवाइजर क्या क्या हो सकता है? 1 2 एंड 4. एंड देखो कॉमन डिवाइजर क्या है? 1 1, दोनों में कॉमन है. सो 1 इज द ओनली कॉमन डिवाइजर. सो वी कॉल दैट GCD ऑफ 3 एंड 4 इज इक्वल टू 1. अगर दो नंबर का GCD कितना होता है? 1 होता है. वी कॉल दोज नंबर्स को प्राइम्स. तो वी विल कॉल 3 एंड we can say 3 and 4 are co-prime numbers. Co-prime numbers, right? So I hope you got this. So UN, so this was the definition. What is UN? UN is a set, okay, where which includes all those numbers, okay, which are co-prime with n, right? Okay, I mean to say all those numbers whose GCD with n is equal to 1. Okay, this is known as addition group, addition modulo n group. Okay, मॉड्यूलर ग्रुप भी बोलते हैं इसको. ओके, so UN is equal to all the elements x such that x and n, GCD of x and n is equal to 1. Now for example, and this forms a group, in fact abelian group. Okay, abelian group under multiplication multiplication modulo n. This is the operation. Okay, this is n. Okay, this forms a group under multiplication modulo n. So you see what is un, u1 is equal to 1 only, u2 is equal to 1, sorry, this is not possible. Okay, because it should be lesser than equal to 1. It is an empty set. So u2 is equal to 1, right? u3, it is equal to zp, it is equal to 1 and 2, which is equal to z2, and this is z3. Okay, same, because here 3 is a prime, so it would be equal to u3. Now u4, these set are, all these sets are group. वन 6 तक सारे एलिमेंट आ जाएंगे, और u8 कितना आ जाएगा? सो u 1 second. u8, okay, u8 8. Okay, so see, these numbers are co-prime with each other, right? So in this set we will be it will be containing 1, 3, 5, 7. Okay, and u9, u9 कितना होगा? You do it by yourself, and also calculate what is u10. Okay, so this is it for today. Rest of the things will be done tomorrow. Thank you.